Hey, my name is Femi from Science Hub and Tech. We're on Chapter 3 now. Okay, so here's the thing. In Chapter 1, we figured out what the real numbers actually are. In Chapter 2, we learned how to talk about collections of stuff. Sets, functions, countability, all of that. But now we're about to ask a question that honestly, reshapes how we do mathematics from this point on. Ready? Here's the question. If I pick a point, just one single dot, and I zoom in really, really close to it, what does the world look like right there, around that dot? Like, is that dot surrounded by friends? Is it all alone? Is it sitting at the edge of something? Or is it buried deep inside? That's the game of Chapter 3. And the name of this game? It's called Point Set Topology. Now I know, topology sounds like some scary alien word. But look, let's break it down. Point just means a dot, a location, a tiny spot. Set just means a collection, a bunch of those dots together. And topology? Topology is, the study of what stays true about a collection of points even when you stretch it, squish it, or bend it, as long as you don't rip it or glue pieces together. And the way mathematicians make that idea precise is by studying which sets are open, which sets give every point inside them a little room to breathe. Don't worry, we'll define open precisely very soon. For now, just know that topology is not about exact shapes or exact distances. It's about, the structure of nearness. What's close to what? What's inside of what? So point set topology means studying the structure of collections of dots, figuring out which dots are deep inside, which are on the edge, and which are being crowded by their neighbors. That's the game. And this is going to matter a lot. Later in this series, we're going to study functions, machines that take numbers in and spit numbers out. But before we can understand how those machines behave, we first need to understand the landscape they live on. We need to know what kinds of territories exist, which ones have walls, which ones are wide open, which ones are, well, compact. Don't worry about that last word yet. We'll get there. Oh, we will definitely get there. Let's go. All right, so before we can talk about dots and neighborhoods and all that fun stuff, we need to set up the stage. Where do our points actually live? Well, think about it. A point on a number line, like the number 3, that's just one number. One single real number tells you exactly where you are. We call that world R1, one-dimensional Euclidean space. It's like, a really long road that goes forever in both directions. You need just one number to say where you are on that road. But what if you're not on a road? What if you're on a field, a big flat playground? Now you need two numbers to say where you are. You need to say how far left or right you went, and how far up or down. That's an ordered pair, like 3, 5. And the world where all these ordered pairs live? That's R2, two-dimensional Euclidean space. It's a flat plane that stretches out forever in every direction. And if you're not on a flat field, but you're like floating in the air, in a room, now you need 3 numbers. Left, right, forward, backward, and up, down. That gives you an ordered triple, like 3, 5, 2. And that world is R3, three-dimensional space. Now here's where it gets kind of wild. Apostol says, and this is actually brilliant, He says, you know what? Why stop at 3? Why not just consider n numbers all lined up in a row? Definition 3.1 says, let n be a positive integer. An ordered set of n real numbers, written x1, x2, all the way to xn, is called an n-dimensional point, or a vector with n components. Okay, so what does that mean? It means instead of giving your location with just one number, or 2 numbers, or 3 numbers, you give it with n numbers, however many you want. And each of those numbers is called a coordinate. It's like one piece of your address. The first number, x1, is your first coordinate. The second number, x2, is your second coordinate, and so on. And the set of all possible n-dimensional points, the collection of every single ordered list of n real numbers you could ever write, that enormous world is called n-dimensional Euclidean space, and we write it as Rn. So R1 is a line, R2 is a flat plane, R3 is the 3D space we live in, and Rn? Rn is whatever dimension you need. It's the ultimate playground. Now you might be thinking, okay, but what's the point of going beyond 3 dimensions? We can't even see 4 dimensions. And that's true. We can't see it. But here's the beautiful thing. The mathematics doesn't care whether you can see it or not. The rules work exactly the same way in 47 dimensions as they do in 2. And by writing our theorems for a general n, we prove them once and they work everywhere. One proof to rule them all. Now, once we have these points in Rn, we need to know how to work with them. How do you add 2 points? How do you stretch one? How do you measure how long one is? Definition 3.2 gives us the rules. And honestly, they're beautifully simple. Equality. 2 points, x and y, are equal if and only if every single one of their coordinates matches up. x1 equals y1. x2 equals y2. All the way down. Every piece of the address has to be the same. Not almost the same, exactly the same. Addition. To add 2 points, you just add them coordinate by coordinate. X plus y equals x1 plus y1, x2 plus y2, and so on up to xn plus yn. It's like if you walk 3 steps east and 5 steps north, and then your friend walks 2 steps east and 1 step north, together you've gone 5 steps east and 6 steps north. You just add each direction separately. Scalar multiplication. If you want to stretch a point by some number a, you just multiply every coordinate by a. So a times x equals ax1, ax2, all the way to axn. Imagine taking your vector, your arrow, and stretching it to be twice as long, or shrinking it to half. Every coordinate gets the same treatment. The 0 vector. There's a special point where all the coordinates are 0. 0, 0, and so on, all zeros. This is the origin. It's home base, the center of the universe. The place where everything starts. Now here come the 2 really important ones. The inner product, also called the dot product. if you have 2 points x and y, their inner product, x dot y, is what you get when you multiply matching coordinates and then add everything up. So x dot y equals x1, y1, plus x2, y2, all the way to xn, yn. It's like a handshake between two vectors, a single number that tells you something deep about how they relate to each other. And finally, oh, this one is huge, the norm. The norm of x, written with those double vertical bars around x, is defined as the square root of x dot x. So it's the square root of x1 squared plus x2 squared plus all the way to xn squared. What does the norm mean? It means, length. It's how far the point x is from the origin. It's the length of the arrow pointing from the origin to x. In 2 dimensions, this is literally just the Pythagorean theorem. You know, a squared plus b squared equals c squared. That's all the norm is. Pythagoras generalized to any number of dimensions. And now watch this. The norm of x minus y? That gives us the distance between 2 points, x and y. It tells you how far apart they are. And that concept of distance is going to be the foundation of everything we do in this chapter. Now, Apostol immediately proves 5 properties about this norm, and honestly, each one makes total intuitive sense. Theorem 3.3 says, let x and y be points in Rn. Then, part A, the norm of x is always greater than or equal to 0, and it equals 0 only when x is the 0 vector. Watch. As this vector shrinks, the length stays positive, 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 and only hits 0 at the exact moment the vector collapses to the origin itself. Lengths can't be negative. That would be silly. And the only point with 0 length is the origin. Part B, the norm of a times x equals the absolute value of a times the norm of x for any real number a. Meaning, stretch a vector by a factor of a, its length gets multiplied by the absolute value of a. Double the vector, double the length. Flip it backwards, same length, just pointing the other way. Part C, the norm of x minus y equals the norm of y minus x. The distance from you to me is the same as the distance from me to you. Distance doesn't care about direction. It's symmetric. Okay, those first 3 were warming up. Now come the 2 that really matter. Part D. The absolute value of x dot y is less than or equal to the norm of x times the norm of y. This is the Cauchy-Schwarz inequality. It says the dot product of 2 vectors can never be bigger than the product of their lengths. We already proved this back in chapter 1. It's a workhorse that shows up everywhere. And part E, the most important one of all. The norm of x plus y is less than or equal to the norm of x plus the norm of y. This is the triangle inequality. What does it say? If you walk from A to B and then from B to C, the total distance you walked is at least as much as if you had just walked straight from A to C. The shortcut is never longer than the detour. Think about it like a triangle. The straight line from one corner to the opposite corner is always shorter than going along the other 2 sides. always. This one inequality, this triangle inequality, it is going to be everywhere. It's the workhorse underneath so much of analysis. Remember it. Love it. It's your best friend now. Next up, we're going to use distance to build something called an open ball. From that one idea, the entire theory of point set topology falls into place. Thanks for watching.